All right, chapter 2, matter and energy. We've talked about matter a little bit. What is matter, though? Formally, what we're going to define it as, matter is anything that occupies space and has mass. Some types of matter are easily visible, like people. People are easily visible. Tables, chairs, etc. Other types of matter are impossible or very difficult to see without magnification. So like a lot of bacteria, air particles, small pieces of dust, individual smoke particles, stuff like that. You occupy space and you have mass. You, the missing word, are matter. A corny little science shirt. If we look at matter, it looks smooth and continuous, or at least it can look smooth and continuous, like the whiteboard feels very smooth and continuous, but it's actually made up of lots of little tiny bits and pieces. It's composed ultimately of atoms. Atoms are tiny pieces of matter. If you want like a frame of reference for how big an atom is, there are about 100,000 atoms in the width of a human hair. So more people than you've likely seen in your life in one place. That number stretched across one human hair. These tiny little pieces of matter can also bond together. They can group together. They can be glued together to form molecules. So molecules are groups of atoms that are joined together. Bonded. It's kind of a rough definition. So put a bunch of atoms together, smash them together in the correct way, get them to interact properly, and you get molecules. So atoms build up to molecules. All matter is ultimately composed of atoms. So this is an example. This is just like a representation of metal atoms. In some substances, those atoms exist as independent particles. So this would be like an example of what like metal might look like. So metal actually exists as individual metal atoms. They're all just sitting next to each other. They're not bonded together to form molecules. In other substances, you get several atoms bond together and form molecules. So this is an example of how we would represent a molecule. So each of these spheres, roughly spheres, is a different type of atom. Hydrogen, oxygen, nitrogen, carbon. And then the sticks, the things between them, those are representing the bonds. We will get to play around with modeling kits a little bit when we learn about Lewis structures. We've got some time set apart for that. I don't remember what this structure is off the top of my head. And that matter, those atoms, those molecules, can exist in different states, different phases. The common states or phases of matter are solid, liquid, and gas. These are the three that we know. Hopefully you know about solids, liquids, and gases. In solids, closely clustered, tightly packed, often nicely arranged. In a liquid, less nicely arranged, they can move past each other, and in gases, they can move freely and independently of each other. We'll talk about each of those individually. So in our solid state, or in a solid state, the atoms or molecules packed close to each other, and they're in fixed locations. They do not move around each other. So some consequences of this is that solids have fixed volume and a rigid shape. You can't compress a solid, at least not very easily, unless there's air particles in there or air space in there, and they have a rigid shape. You don't have to worry about, for example, setting your Apple Pencil down and it melting off the countertop, right? It might roll off the countertop, but it's not going to melt. The analogy that I like to use for the solid state is this is like people at a movie theater. So people representing the atoms at a movie theater, assuming the movie's playing. Usually when you're at a movie theater, you have a seat. Hopefully you have a chair somewhere you're sitting. And for the duration of the movie, unless you have to get up and go to the bathroom to refresh your snacks, everyone in the movie theater is sitting in their own spot. Are they all completely locked in place, not moving while watching the movie? No, they're going to be moving around a little bit. They might be fidgeting, they might be eating their popcorn, they might be eating their Milk Duds, whatever candy you like, drinking their soda, chatting with their neighbor, being on their phone, whatever people at movie theaters do, right? But they are stuck, locked in their position. They're not swapping seats with their neighbor. They're not getting up and moving to the front of the movie theater usually. So people at a movie theater behave like atoms in a solid, or in the solid state, or molecules in the solid state. They're kind of locked into their position. Usually they're about packed in as close as they can be to each other. There's two types of solids, or one way that we can categorize it is two types of solids. There's crystalline solids. These form crystals. So crystals exist because the atoms or the molecules arrange in a long-range repeating order, so they're patterned. What this means is that if you zoom down to the atom level, the molecule level, and you looked at one spot of this solid, a crystalline solid, and then you scanned over some amount, you'd be able to get those images to overlap. They would overlap perfectly. It's the same structure repeated over and over and over again. So this is a representation where we've got oxygen and silicon. This is a representation of the crystal structure of quartz. So in quartz, like rocks that you find maybe outside or pretty crystals that you see in stores, it's got this nice long-range repeating order. This is also why crystals of different types form kind of roughly the same shapes, and they'll often have the same facets on them, is because of that nice long-range repeating order. They just like to form those shapes. If you arrange the oxygen and the silicon into a different arrangement, an amorphous solid, so if there's no order, if it's not repeating the same pattern, then instead of quartz, you get glass. So not all glass is going to be like this, but generally glass is an amorphous solid. It's a lot easier to get it to form this amorphous solid, where if you zoom in at the atom, the molecule level, and you take a picture, and you scan over, you would not be able to get those images to overlap because it's not repeating the same structure. This is generally easier to form, and the crystal structure is a little bit more difficult for us to recreate. So crystalline structures have long-range repeating order. Amorphous solids don't have long-range repeating order. You can't get the images to overlap. Moving on to our liquid state. In our liquid state, the atoms or molecules are still close to each other. I'll often refer to this as touchingly close. They're close enough that they can interact with their neighbors and reach out and touch somebody. But where they're different from solids is they're free to move around each other. So they are swapping places with their neighbors when they're in the liquid form. And this is why liquids run and roll. Like they'll flow downhill because they can move past each other. They're not fixed into their shape. Because of them being touchingly close, liquids have fixed volume. Because there's no empty space between, no empty or free space between them. Again, because they can move past each other, they're free to move relative to one another. They can move past their neighbors independently of their neighbors. Liquids assume the shape of their container. You're not going to ever accidentally, like you fill up your water bottle and then you go to pour it out and it's just stuck in that same spot. It's not going to keep that same shape. It's going to run out of the water bottle. These two properties, the fixed volume, not being able to compress it, and them being free to move around each other, is why hydraulic presses are so effective. They use a liquid. You can compress a large area of the liquid, so like a massive area of the liquid, and then funnel all of that force down into a small spot, and that gives you the power of hydraulic press, which I think is fun and cool. My example for a liquid state, this is like people at a concert. In the front rows. We're not talking about like the Fresno Philharmonic concert where everyone's sitting in their seats nicely. That's more like a solid state. We're talking about like if you go and see Sabrina Carpenter, I'm assuming that there's people all piled up at the front of the stage, or if you go see Chappell Roan or whoever you like. The people that are all packed up in the front trying to get close to their favorite celebrity, their favorite singer, there's no space between them. And they could also move around each other, right? Sometimes people are going to like, I'm going to squeeze up to the front for this song, or hey, I need to go get my friend, they need help, or I need to go use the bathroom, or I need a drink of water. You can always filter your way past those people. You can swap places with people when you're up in the front at a concert, or so I've been told, or so I imagine. So that's more of a liquid situation where the people, again, are the atoms or the molecules. And then in a gas state, the atoms, the molecules, are separated. So there's empty space between particles. Particles, atoms, molecules, what have you. So this is different from our solid state. This is different from our liquid state. Those two were both touchingly close. In our gas state, there's empty space between them. And because of that, gases are compressible. When you compress a gas, you reduce the empty space. You're forcing those particles to be closer to each other. If you do that enough, then you get a liquid or a solid. Because of this, gases always assume the shape and volume of their containers. This is something you may have experienced if you're driving in the car with somebody and you pick up fast food because somebody's a little snacky. You get some Taco Bell. Even if they're in the back seat and you're in the front seat and you don't have the air on, you'll end up smelling whatever they're having. Right? Those smell particles make their way over to you, or if somebody in the classroom were eating a particularly odorous fish, for example, they decided to open up a can of sardines, the rest of us would eventually also be smelling those sardines, even though we're not sitting right next to them. Those smell particles wafting and making their way through the room. The gas state is kind of what y'all are like after class is over. When we're in class, It's sort of a solid state. You're kind of just sitting in your spot. You're writing, taking notes, you're thinking, you're falling asleep, whatever you're doing. And then once class is over and you're free to go, it's the gas state. You go out and fill up the world and go your separate ways. And there's lots of empty space between most of you, at least. Here's a table from our book that's got a couple of the comparisons. So for our characteristics, for the shape, our solids have a definite shape. Our liquids and gases do not have a definite shape. They'll take the shape of their container. Our characteristic of volume, solids and liquids have definite volume. You can't compress them. Our gases have indefinite volume. You can compress them. If you finish off your $1 water bottle or 99-cent water bottle or whatever, and you squeeze the body of the water bottle, it builds up pressure. You're compressing the gas. You flick the lid and it goes flying into your friend or into the sky or wherever you're directing it. They're compressible. Relative intermolecular interaction strength, we'll talk about that later in the class. And the relative particle positions in contact and fixed in place solids. They're not moving around. They're not swapping places with their neighbor. That's like here in lecture or in a movie theater. For liquids, they're in contact. They're close. They can move past each other. That's kind of more like what we'll be doing in lab. You can walk past your neighbors. And gases, that's when we're done with class and you go home and go your separate ways. Questions so far? Other ways that we can classify matter. So we've classified matter by its state, solid, liquid, gas. We can also classify it based on its composition, what it's made of, or what's in it. Keep telling myself one of these days I'll write all the letters in order every single time. Hasn't happened yet. So we've got two options for composition, for what it's made of. We can either have a pure substance. A pure substance is only one thing. We can also have a mixture, which is not only one thing, it's two or more things. Some types of cereals, like Honey Nut Cheerios, more of a pure substance. It's the same piece of cereal repeated over and over and over again. That's all that's in the box. Things that are a mixture, more like Lucky Charms. You've got the not so interesting parts, and then you've got the Lucky Charms exciting part that's in there, all the different shapes, the marshmallowy parts. Right, so Lucky Charms would be more of a mixture. Honey Nut Cheerios, Cocoa Puffs, things like that, more of a pure substance. And within pure substance, one type of atom or molecule, and mixtures, two or more things. We also have further classifications. And we'll go into detail on some of these. So within our pure substances, that's where we'll start first. So looking at just one type of thing, we have elements. Elements are on the periodic table of the elements, often just called the periodic table. We have a periodic table here in class. You've also got one on your yellow sheet. You'll also have one on your information sheet on exams. Elements each have their own box on the periodic table. So on our periodic table in the class, each of those individual boxes is a different element. Most of them exist. Some of them do not currently exist as far as we know. An element is a pure substance. It can't be broken down to be any simpler than it is. Elements often exist as atoms. Another way of saying it, an atom is the smallest piece of an element. You can't get any smaller than one atom of an element. And all 118 of our known elements are listed on the periodic table. There are also compounds. Compounds are a different type of pure substance. Compounds are two or more elements that exist as molecules or some other combination of things. So combination of elements. So put a couple of atoms together of different elements and you've got yourself a compound. There's different types of compounds as well. We'll talk about those, I think, in the next chapter. And compounds can be decomposed into simpler substances. They can be broken into atoms or elements. So water, for example, is made up of hydrogen and oxygen. If you run an electrical current through a sample of water and it's the right, voltage and everything, you can actually separate the hydrogen and the oxygen of water in a process called electrolysis. Not recommended to do at home because you would also probably produce chlorine gas, and hydrogen and oxygen gases are explosive. So it's like a whole lot of things that could go bad. But you can do it. You can do it, just don't do it. A mixture, on the other hand, compared to a compound, these are not chemically united. They're just kind of in the same area. These can be separated without breaking them. Without breaking the molecules/compounds. So an example of element would be something like carbon on our periodic table. Pure carbon has a couple of different forms. One of those forms is the graphite that you use in your mechanical pencil or just in a regular pencil. Another form of carbon is diamonds. Diamonds is another form of just carbon. It's just the element carbon. There's probably conclusions that it's purest. A diamond is just carbon. For compounds where we've got things mixed together, two or more elements, that would be things like table salt, sugar, lots of other things that I'm forgetting, rust, different sorts of like alloys and things. Might also be examples of compounds. Maybe not alloys, but rust for sure. Examples of mixtures, things like salt water, or sand and water. Right, those are things that are mixed together. In the case of salt water, it's salt and water. You can separate out the salt and the water. So you could do some desalinization. You can evaporate all of the water and the salt will be left behind. And then you could collect that water somewhere else. That's what they do for water processing on the coast. It takes a lot of energy, but it does separate the water and the salt. You might also do like a reverse osmosis might work, where you squeeze the water through tiny little pores and the salt isn't able to go through it with it. That would be another way of separating them out. In the case of sand and water, you could probably just pour the water off the top, or get like a coffee filter and just pour everything through that. The water will go through the coffee filter, the sand will get caught by the coffee filter. So those you can separate out pretty easily. You don't have to like run electricity through it. You can just heat it up or run it through a filter. Those are mixtures. We can classify mixtures by how uniformly or how evenly they mix. So a homogeneous mixture is going to be the same consistency throughout. The same thing throughout. So if you take a sample from one area and you take a sample from another area, they should be approximately the same. So things like lemonade. Assuming that you mixed your lemonade, if you take a sip from the top of your lemonade and a sip from the bottom of your lemonade, they should taste the same. It's not going to be you take a sip from the top and it's all lemon juice, and you take a sip from the bottom and it's all sugar. It should be the same consistency throughout, otherwise you need to make your lemonade better. Other things like bronze and steel and air and all the other sodas would also be examples of homogeneous mixtures. Some soups are also homogeneous mixtures. Every little spoonful, every little slurp is the same soup. Heterogeneous mixtures, hetero being opposite or different, heterogeneous mixtures have a composition that's not uniform. Different parts have different ratios, for example. Ratios of components. So like marble countertops often have like swirly patterns to them where they've got like fun colored areas, inclusions. It's not just the same like thing throughout, like the whiteboard, right? It's the same consistency all the way through. Or like our carpet has different consistency. Right, you take one section of carpet and it might be this like Orange Go Tigers sort of stripy section. If you look at another part, it might just all be the gray and blue. That's going to be a heterogeneous mixture. Other examples, I'm going to cross out soup and swap that for stew. Or chicken noodle soup would be a good example. Hopefully your chicken noodle soup has a heterogeneous consistency to it. You might take one bite, you get a little bit of noodle, you take another bite, ooh, I got some chicken. You might take another bite, oh, it's all broth. Hopefully that's the experience that you have with chicken noodle soup. If your chicken noodle soup is a homogeneous mixture, I've got concerns. Because that would mean that you blended it and like the meat is all blended into the soup, and that just sounds really gross. Another example of a heterogeneous mixture is like vinaigrette salad dressings, so the ones that you have to shake up before you use them. If you don't shake them up before you use them, it's like, ooh, I got all olive oil this time. Or, ooh, I got all balsamic vinegar this time. Stuff like that. Those are examples of heterogeneous mixtures. Right, you have to shake it before you use it to get it to recombine. Mustard can sometimes be a heterogeneous mixture if it's been sitting too long in your fridge or wherever else you store your mustard. All right, classifying matter. Let's do our best to identify each of these substances as a compound, an element, a heterogeneous mixture, or a homogeneous mixture. Let's start with a stuffed animal shark. Is a stuffed animal shark a compound, an element, a heterogeneous mixture, or a homogeneous mixture? It's a heterogeneous mixture. If you were to cut up the stuffed animal shark, part of it would be the cover. There'd be a lot of fluff on the inside. It's not going to just be the same consistency throughout. You might chop a portion of it off and you've got like the beady little eye looking at you wondering, why did you chop me up? So that would fall into a heterogeneous mixture. How about coffee? Is coffee a compound, an element, a heterogeneous mixture, a homogeneous mixture? It's a homogeneous mixture, hopefully. It's a homogeneous mixture because there's water in there. There's maybe a little bit of coffee grounds. There's all the compounds in the coffee, things like caffeine, often why we drink the coffee. The stuff that makes our teeth brown, that makes, gives the coffee that color. This other stuff that makes it bitter or makes it sweet or makes it taste good or bad. So there's a bunch of things mixed together, and hopefully every sip is about the same, homogeneous mixture. What about the alcohol, if you have a thermometer that has alcohol in it? What about the alcohol that's in a thermometer? Yeah, that would be a compound. It's some sort of alcohol. They're usually colored, so it really would be a homogeneous mixture, but if we're thinking about just the alcohol that's in the thermometer, the alcohol part is a compound. How about selenium? Selenium is an element. How do we know it's an element? It's on our periodic table. So if you look at your periodic table on your yellow sheet, you look over in the kind of the more to the right side, you'll find the symbol Se. It's got a number 34 above it. That is selenium. If it's on the periodic table, that means it's an element. Otherwise, it's something else. Questions about the ways that we've been classifying matter so far? All right, here's a little summary slide. All right, so we can separate matter into either a pure substance, it's just one thing, or it's a mixture, it's more than one thing. If it's a pure substance, it's either an element, it's on the periodic table, or it's a couple of elements, it's a compound. Our mixtures can either be homogeneous or heterogeneous, homogeneous mixtures being that nice smooth consistency throughout. Every bite is the same, every sample is the same. A heterogeneous mixture, you're going to have different layers, like sand in water. Your mixtures can be mixtures of elements, it can be compounds, it can be a combination of both. With matter, we've got properties, physical and chemical properties. These are characteristics that distinguish the substances. So properties, characteristics of a substance. This is similar, this is like our, for atoms and molecules, characteristics are kind of like personality traits for humans. Some people are really quirky, some people are really fun, some people are really bright and lively, other people are really boring. That's just the way that they are. Some substances have different characteristics, some have the same. So we'll talk about a couple of those. There's physical properties. Physical properties are displayed without changing its identity. So if you observe a physical property, it was the same thing before you observed it and after you observed it. One example of this would be the smell of gasoline. If you go to the gas station, you're pumping gas into your car, your motorcycle, your truck, and you accidentally smell a little bit of gasoline, have you suddenly transformed the gasoline into something else? Or is it just still gasoline? Hopefully it's just still gasoline, right? You haven't magically transformed all the gas that you just paid for into like water in your truck or in your car. So smelling something, tasting something, the color of something. My shirt today has pink and white and red in it. Now that we've observed it, does it still have pink and white and red in it? It sure does, right? Physical properties, we can observe them, nothing changes. So observing a physical property doesn't change the substance. doesn't change the substance, the whatever it is. Other things like density and melting point are also physical properties. Chemical properties, on the other hand, are only displayed through changing identity. So observed by changing the substance. So for example, the flammability of gasoline. In order for you to observe that gasoline is flammable, you have to burn it. After you've burned your gasoline, is it still gasoline? Can you cycle the exhaust from your car into your gas tank and just run your car forever? No, unfortunately not. Otherwise, we would have probably figured that out and we would be doing it. So observing the flammability, the combustibility, the explosiveness of gasoline, it has to turn into something else. Hopefully it's just carbon dioxide and water in the case of gasoline. Other things like corrosiveness, acidity, toxicity, those typically involve changing the identity. In order for an acid to dissolve a piece of metal, some of that acid has to get used up. Okay, so physical properties. The atomic or molecular composition does not change. It's the same thing before and after when it displays these physical properties. The melting point of water, the temperature that water melts at, or any phase change, any change between states of matter, is a physical property. So melting, freezing, boiling, condensing, and sublimation, those are the 5 that we talk about in this class. Those are all physical. If you melt water from ice into water that you can drink, you could freeze it back and it turns back into ice. It's the same water before and after. All that you've changed is just how it's related to each other. The particles either can't move past each other or they can move past each other. Candle wax, the thing that burns when you burn a candle, is that flammability is a chemical property. That wax has to change into something else. You have to use up a little bit of your candle in order for you to be able to get the full smell, the full aroma, the full aura of the candle. So let's think about whether each of these properties is physical or chemical. Is it not changing what it is, physical, or is it changing what it is, chemical? So the explosiveness of hydrogen gas, is that a physical or chemical property? It's a chemical property. In order for the hydrogen gas to explode, we have to light it on fire. It turns into water, reacts with oxygen in the air. How about the bronze color of copper? Is that a physical or chemical property? Physical. If you look at a piece of bronze or a piece of copper and you observe, wow, it's a bronzy color, it's a coppery color. It's still that same coppery color. You haven't magically transformed it from copper into something else. The shiny appearance of silver. Also physical. How about the ability of dry ice to change from a solid directly into a vapor, a gas? It's also physical. It's one of the phase changes that I mentioned earlier. We have questions about physical or chemical properties? Related to those physical and chemical properties are physical and chemical changes. So in physical changes, the matter changes its appearance, so like changing from ice to water, for example. But at the molecular level, at the atomic level, it's still water molecules. They're just arranged a little bit differently. So it's the same chemical before and after. Nothing's changed at the chemical level. In a chemical change, the matter does change its composition. So it's a different chemical before versus after. An example of this would be copper turning green when it's exposed to air. So like the Statue of Liberty was originally a bronzy coppery color because it's made of copper, but they just let it sit outside, and so naturally it got exposed to sea, water, air, and so now it's this iconic green color of the copper oxide. So that's a chemical change that it went through. So for physical changes, state or phase changes are always physical changes. So solid and liquid, either direction, and liquid and gas, again, either direction, and solid and gas can also switch directly between each other. So if you buy dry ice at like the grocery store or something, that's solid CO2, and it actually converts directly to gaseous CO2. You can also get some gases to go directly to solids. These are always going to be physical changes. Chemical changes result in new chemicals being formed, or different chemicals being formed. And these happen when we go through a chemical reaction, which we're going to talk about a lot in this class. Lots of chemical reactions in this class. And we often diagram our chemical reactions with something like this. So we'll have our reactants on the left side. Reactants, shockingly, things that react. Things that combine together and then they form something else are products. The products are what the reactants make. And then we typically have a single-headed arrow showing that we're moving from the reactants to the products. Sometimes we do have a double-headed arrow. Some reactions can go both ways. And for this class, we don't typically include any extra information above or below the arrow, but you will see that occasionally that indicates things like other chemicals that are present but not super important, a catalyst that's used, temperature, other things like that you'll typically see in like organic chemistry. So our reactants, things that are on the left side, products, things that are on the right side. I'll usually use left side, right side, reactants, products interchangeably. Okay, some examples of physical changes. We talked about changing between states of matter, solid, liquid, and gas. You can also do separation of a mixture, like separating sand and water. There can also be physical changes of deformations, so cutting something, denting it, stretching it, like when you're making wires or if you're cutting a piece of paper. If you cut a piece of paper, both the pieces are still paper. It's just that they're not right next to each other anymore. Making solutions, so kinds of mixtures, putting like table salt in water is actually a chemical change. But making sugar water or simple syrup. The reason that the table salt dissolving is different is because table salt is sodium chloride, and the sodium and the chloride parts actually get pulled apart when they dissolve into solution. So it's actually existing as different things in solution, whereas sugar dissolving in water, the sugar molecules stay intact. You're just separating the different sugar molecules from each other. Some examples of chemical changes or some signs of chemical changes include temperature change, like those little hot, I forget what they're called. What are they called? Hot Hands? Is that the brand?
Hot Pockets.
Hot Pockets are tasty. But no, that's not what I was thinking of. Like the heat pads or cold packs, like instant ice packs, those temperature changes indicate that there might be a chemical change going on. If light is produced, like in glow sticks, that's a sign of a chemical change. You have to break something and it mixes inside of the plastic container, and then it produces light. Color changes are also signs of a chemical change, like that copper turning green. Copper is Cu for the symbol. Or if you've got, like if you accidentally leave some steel out, or if you've got a cast iron, right, and you leave it in the sink for too long and it's not coated well and it starts to rust, that's a sign of a chemical change as well. If there's bubble or gas, bubbles are gas that's formed but not from boiling. Like if you mix two things together and bubbles come out, like if you mix baking soda and vinegar, those bubbles that get formed from that, that's a sign of a chemical reaction. If there's a change in the way that something smells or tastes, like if you're making caramel, the color change of the caramel as you make it, this is probably super unrelatable, but when you're making it, the taste changes as you do it. When you burn something, oops, I cooked my meat too long, oops, I cooked my veggies too long, that change in taste, that's a sign of a chemical change. And then another sign of a chemical change would be solids forming when you mix two clear liquids. Almost done. Let's think about some of these, whether they are physical or chemical changes. If you are boiling water, is that going to be a physical or a chemical change? It's a physical change. It's a physical change because it's a state change, it's a phase change. It's just a phase. We're changing from liquid water to gas water. What about a nail rusting? That's a chemical change. It's changing color. It's changing the consistency. It tastes different. Hopefully you're not tasting it, but it probably does taste different. It probably smells different too. Let's say that we mix a green solution and a colorless solution, and the resulting mixture is pale green. This one would be a physical change. Probably a physical change because the color changed, but we mixed a colorless liquid and a green liquid, so we just diluted the color. This would be like if you're making up, I don't know, green beer for St. Patrick's Day or something, and you're putting green food dye in. The green food dye is really concentrated, and it dilutes when you put it into whatever food or drink that you're making. Let's say that we mix two colorless solutions, and the resulting mixture has a yellow solid, a yellow precipitate. Is that physical or chemical? Yeah, that's right, it's chemical. Somebody was thinking it. The reason that this is a chemical change is that there was a color change. So two clear things resulted in something that was yellow, and there was also a solid formed. From two liquids, or from liquids, without like freezing it out. Any questions about physical, chemical properties or changes? These, especially these last couple of slides, will be very helpful for you completing your pre-lab for tomorrow. So it's great that we got here. All right, that'll do it for lecture for today.